All right, so today we're going to talk about inverses and determinants, and this is actually a really important skill moving forward to what we're going to use matrices for tomorrow, which is going to be solving equations. So today we have a few vocabulary words we need to really focus on: inverse and determinant. So let's start with what an inverse is. The inverse is defined as two matrices that multiply by each other, so a matrix and its inverse. And when you multiply, you get the identity matrix. So for instance, if you multiply a matrix and its inverse, so the original times its inverse, you will get the identity matrix. And remember, the identity matrix is kind of like that reduced row echelon form where you have the ones that run diagonal. This matrix could be, you can have any size square matrices, but it is required that matrices be square, so that's something to note. Inverses can only be determined for square matrices, and even still, not all square matrices have inverses. So we'll talk about when that exists and when that doesn't exist. Today we're going to focus mostly on 2 by 2 matrices. That's why that says that here, mostly on 2 by 2. But I will show you how to find larger matrices because that will be relevant later on to solving different problems. All right, so we're going to need to take really good notes right here because I've got some formulas to show you. So the first one is about the determinant of a matrix. So the determinant is denoted DETA. You will notice when we go to our calculator that there is an option to find that in there, but as you know, we need to be able to do this by hand. And it is found by taking, if we look inside the matrix, this is the formula right here, AD minus BC. You multiply this diagonal, and then you're going to subtract the multiplication for this diagonal. Now, we need to know that for when we go to find the inverse. So the inverse formula is going to be, first, it's going to exist only if the determinant is not equal to 0, so you need to make a note of that. We denote it just like you would expect inverses, this little like -1 notation. And it has an inverse. If it does have an inverse, it is set up this way. So let me zoom in and explain this formula to you. It is 1 over the determinant of A. So this is like the reciprocal of the determinant, 1 over the determinant of A. And then notice the pattern that's going to happen. What they've done in this area is they have flipped these two or switched these two. And then for the other diagonal, they have negated these. And that is based on the original matrix. I'm going to zoom back over here. That is based on this original matrix. So you should have the original and this formula for the inverse written in your notes. So let's practice finding a few inverses. The first step in finding the inverse is going to be to find the determinant. So the determinant of A here, remember we're going to take the two diagonals and multiply them. So that's going to be 4 times 2, which is 8. Minus this other diagonal, so minus -1, which is going to give me a determinant of 9. Then to find the inverse, I'm going to do 1 over the determinant, so 1 over 9. And now, remember I need to switch these two and negate the other two. So instead of 4 and 2 in this spot, it's going to become 2 and 4. And then for the other spot, and it's kind of hard to see on this one because those are negatives, but for that other diagonal, we're going to change the sign. So up here in the top right, where that says +1, it's going to be -1. And in the bottom left, where it says -1, I'm going to change that to a +1. This can be simplified. Sometimes they leave it written like this, so sometimes this just is the answer, but it can also be simplified to a single matrix, which would make this 2/9, -1/9, and this is me distributing this 9, 1/9, or sorry, the 1/9, and 4/9. And you can check that this is actually an inverse by multiplying the original by this. So I'm just going to make a note of that. We could check this by completing the multiplication. 4, 1, -1, 2, times 2/9, -1/9, 1/9, and 4/9, and when we multiply those, we will in fact get, and you could use your calculator to prove to yourself, the identity matrix 1, 0, 0, 1. All right, so if we try another one here, again, we're going to start with the determinant. So the determinant is my first diagonal multiplied, so 24, minus my second diagonal multiplied, which was 24. In this case, 24 minus 24 is 0, so my determinant is 0. If that doesn't register any warning flags to you, you might continue and say, okay, well, the inverse is going to be 1 over the determinant. And then we would go to set this up. So remember, on my first diagonal, I'm going to erase this so you can see. On my first diagonal here, I'm going to switch the values. So this is going to become a 4 and a 6. On the second diagonal, I'm going to negate the signs. So the 8 will stay up there, but it will become a negative 8, and the 3 will stay but become a negative 3. All right. Now, if I were to try to simplify this and move forward, if I try to multiply by 1 and divide by 0, I'm going to start getting an error because you cannot divide by 0. So because you cannot divide by 0, that means that the inverse does not exist. All right, so that's the bulk of our lesson. I do want to show you a few applications of that, though, so take some notes on these two. We can use determinants to find the area of a triangle. Sorry, I meant to highlight that. And I want you to write these things down. So if you are given these two vectors, that will create a matrix A, B, and C, D. Remember that we set matrix for ordered pairs up, X, and then Y, kind of like a horizontal table. I know that's weird. Then that can create this picture of AB is here, CD is there, and so if we connect them like we did with addition, we get this triangle here in the middle. All right, so this is what we're talking about, is this triangle here in the middle. You do not need to pay attention to these other formulas or even draw them necessarily, but I would maybe draw this diagram. And so what we see with vectors is that we can find the area by this formula down here, and that is the area of the triangle is equal to 1/2 times the determinant of that matrix that we created. All right, so let's do an example of that. This says a triangle is defined by 4, 3, 3, 4, and -1, -2. So we're going to start by writing a matrix, 3, 4, -1, 2. And we need to find the determinant of this matrix. So the determinant is going to be 6 minus -4, or 10. And so the formula for the area of the triangle is equal to 1/2 times the determinant. So in this case, that's by 10. So my area of my triangle would be 5. Similarly, we can use that to find the area of a parallelogram. So in this example, so again, I would like for you to write this down. We are given a parallelogram defined by these two vectors. Those are these vectors right here. And notice this would be if we created a triangle and then doubled it over, so it creates this entire parallelogram. So I'm going to start by finding the determinant. So my determinant, let me actually name the matrix first. The matrix itself is 5, 7 to -5. That means my determinant is going to be my first diagonal, -25. 25, sorry, minus my second diagonal, which is 14. That's going to give me an area of determinant of -29. Now, the formula we had before for the fraction, or for the triangle, was just for half of this. So if I have two triangles, I'm going to double that, which means this right here is the area of the full parallelogram. One thing to note is that because we're talking about area has to be positive. So the area is not going to be -29. The area in this case is actually going to be positive 29 for the parallelogram. And that's all we have for our video today.